Hey everybody, Mr. Stewart here, and welcome to this screencast that's going to help us finish with the topic of exponential decay. So let's take a look back into our notes. As you can see, last time we started off by reviewing what constituted a growth rate and a decay rate, as well as determining both growth and decay factors. So you might recall last time we were working here at the bottom of this particular slide, and we detailed what exactly is considered a rate versus a factor. So the rate, or the percentage or decimal, is typically given in the problem, and the factor is what we have left following subtraction from 100%. Okay, so the rate is the percentage lost versus the factor as the percentage remaining. Okay, so just remember the decay factor is the percentage that's remaining. So let's take a look at our final example that's going to showcase the concept of exponential decay. And a great example of that is that of car depreciation. So as you can see here, we're buying a vehicle for $20,000. It's losing 15% of its value every year, and there are a few things that we need to take care of. Firstly, we need to come up with an equation for this particular function that's going to model or represent the loss of its value year over year. Okay, so recall last time we went through and we created a model or an equation as a model. We started out with the base, or the generic equation, f at x equals a, which is the initial value or y-intercept multiplied by b to the x. Now the b, or the base, in that power of b to the x is either the growth or decay factor. In this case, it's going to be the decay factor in our problem. So to make it more contextualized or real world, let's let v sub 0, sometimes called v naught, be the initial value, whereas v is going to be the depreciated value. So depreciated value can be thought of as a discounted value, a remaining value, or the cost of something, in this case a vehicle, after it's lost money. So the rate was given as 15%, which means that our factor, or decay factor, must be 1 minus the decimal equivalent of 15%, or 0.15, giving us a decay factor of 0.85. Now the exponent x is going to represent the number of decay periods. Okay, so year over year, we're going to be determining how much the car is depreciating. So the exponential function that we can use to model the vehicle's depreciation would be none other than v equals v naught, or the initial value of the vehicle, multiplied by 0.85, that's the decay factor, to the power of t. So as you're going through this particular video, take a moment to pause and or to rewind to consolidate some of your thinking, as well as to finish off notes. Okay, so do make sure that you're taking time to write your thinking out. Okay, so moving forward, the other two parts of the problem, part B, let's take a look at what the car will be worth in 5 years. Okay, so after 1 year, we'll lose 15% or maintain 85%. After the second year in, we'll lose another 15%, or we'll retain 85% of that reduced value, and so on and so forth. So that's particularly how exponential decay works. So if we set t, or the value of the exponent, as 5 and evaluate, we should have ourselves the depreciated value. So here's a great opportunity to work with the calculator. So I'll show you a couple of screenshots that I have. So notice that my first step here is to work with the power. So 0.85 to the 5. So I'll hit equals after that, and you can see I have this long decimal here, and I'll multiply it by the initial value. So that decimal is going to scale the $20,000 down to give us approximately $8,874.11. So amazingly, and perhaps a bit saddening, after 5 years, my $20,000 car, provided it's in decent shape, is going to be worth just under $9,000. So once again, if you need a few moments to study the solution and to copy it down, do pause and take that time for yourself. Well, last but not least, we have our final part of the problem, and much like we did in the first example involving exponential growth, this one here is going to take a little more time and require a little bit more writing, so you might need to pause more than once. So we're being asked when my vehicle will be worth only 10% of its original value. So that is 10% of the original $20,000. Well, if we find 10% of that, that's $2,000. So in this case, the remaining value, or the value of V, is going to be $2,000. Okay. Now to simplify, what we need to do is to isolate the power 0.85 to the t. And that'll make finding t that much easier. So if we divide both sides by 20,000, the 20,000s will cancel from the right-hand side, and we're left with 1/10, or 0.1, on the left-hand side. Now moving forward from there, what we'll do is then we'll apply two different methods to this equation up here. So 0.1 is equal to 0.85 to the t. So beyond an algebraic method, which we can study at some other point in time, also in different math courses, you might see it post-secondary, we're going to use two different methods. One is called systematic trial, and you're very accustomed to that, and we'll use graphing technology, or Desmos, to try it again. So with systematic trial, I like to set up my work in the form of a table. It just works well for me as an organizer. And I'm going to start with a value of 10 years. Okay, so seeing that in the last part, after 5 years, we were just under 9,000, I'm going to go up to say 10 years, and I'm going to give it a try. So what I want to do is, after 10 years, I need to see my equation equal and backtrack that a little bit here. I'm just going to cover those again. I need my equation to be equal to, that's what I wanted to say right here, 0.1. Okay, because that 0.1 is the value of the vehicle, the remaining or reduced value, the $2,000. So if I substitute the value of time in for t and evaluate, I get 0.1969. So that's still too large, meaning that my vehicle hasn't yet lost enough money, okay, to bring it to $2,000. Now, if I up that, let's say I go another increment of 5, so 5, 10, 15, okay, what that's going to do, after substituting in the 15 for the exponent, I end up with 0.0873. So that being much less than 1, I've lost more than what I'm looking for. So somewhere in between 10 and 15, now if we approximate 14, we'll end up with 0.1027. So still not quite enough, but for the purpose of systematic trial, that's a good approximation for us. So the value of the vehicle is now nearly $2,000. So we can conclude that it'll only be worth 10% of the original $20,000 in about 14 years. Now, if we want to try to add a bit more precision, we can use technology to give us a hand. And I'll take you online right now and show you. Let me bring up Desmos here. There's our NG Math page, by the way. You just need to search NG Math in order to get there. So now let me show you here what I've done. You can see I've plotted two functions. So y equals 0.1 was the left-hand side of the equation, and y equals 0.85, I'm using x now instead of t, was the right-hand side. So the idea is that we trace along the graphs, so both red and blue, until we hit a point of intersection, which is 14.168. Okay. Another thing you can try too with Desmos, and I really like this feature. Now I'll go into my settings and I'm going to duplicate my function. Okay, and then what I'm going to do is create a table out of it. Okay, so now if we look at the table, you can see it's plotting all of the y values. Now we know that at 14, we end up with 0.1027. And then at 15, we end up with 0.08. So Desmos is doing a really great job in showing us that region graphically, that we know there's still a bit of a gap there. So we know it's not 14 years. So if we really wanted to, we could add in, say perhaps 14.1, and we're still too much. And if we go to 14.2, right, we're almost there. So it's between 14.1 and 14.2, and just to give it a try, I'll go 14.15 to go in between, and that's relatively close. So you can see over here, we're really squeezing in or moving in along towards that point of intersection. Okay, so that's another way you can use Desmos in a table feature in order to find points of intersection. Okay, or to solve other problems if needs be. So moving back to the problem. Okay, if you need to sketch a graph, here's something that you could take down. So again, it shows the function, the equation. Let me backtrack to that there for a second. It's showing this equation here, okay, 0.1 equals 0.85 to the t, which is kind of that reduced version of the original equation. It's plotting it as two separate functions, a horizontal line intersecting with an exponential decay curve, and we're approximating. Actually, this is quite good to 3 decimal places. Desmos is giving us the point of intersection.